All right, hi guys, it's Justin here. This is week 2 of Chemistry 4, so this is our second video of the second week. Now, there's only 2 videos this week, okay? Last week, which was week 1, we had 3 videos. This week, we only have 2 videos. All right, so with this, you will have after this second video, you'll have all the homework problems you need for weeks 1 and week 2. And then maybe next week I'll put together a video where I do some of the homework problems for you. Seems like I've been getting some questions on how the homework questions are asked, but they come directly from your textbook. Okay, so you do need your textbook. All right, let's get started. Page 1, periodic table. So we're just going to make a few bullet points on some of the different groups of the periodic table today. Then we're going to go into something called electronic structure of atoms. So the periodic table at the top says, remember metals, nonmetals, and metalloids? We talked about those and where they were located in the periodic table. Well, periods are horizontal rows. There's 7 periods across the periodic table. And in groups, there are 18 vertical groups. All right? Now, the actinides and the lactonides are down at the very bottom of the periodic table, separated. They don't have a group. So, some important groups are group 1, the alkali metals. These are shiny, soft, very reactive, and they react with air and water. So when they're stored, they're actually stored in oil because they're so reactive. Group 2 are the alkaline-earth metals. These guys are also shiny, but less so, and then they're also less reactive than the group 1 metals. They do react with water, but they don't react with air, so the alkaline earth metals are things like magnesium and calcium. Alkali metals are things like lithium, potassium, sodium, group 1. So group 1 and group 2 are so reactive that they're not found in their pure states in nature. They're usually found in compounds. Group 17 are called the halogens. That's the far right column, not all the way. It's the second to the last far right column. Halogens, these are things like chlorine, fluorine, bromine, iodine. These guys are colorful, corrosive nonmetals, usually found in combination with other elements. Then group 18, very far right, noble gases. Noble gases used to be called inert gases because they're very unreactive. They like to be by themselves. But they're very colorful. You find them in some of our lights, things like xenon, and other ones are krypton, helium, argon, etc. All right, now I want to talk about the major focus of today. We're only on page 2 of our notes here, right? So most of today is dedicated to this next topic. I got a little star with a circle around it. It's called the electronic structure of atoms. Your book refers to this as electron arrangements. Okay, so some background first, electronic structure of atoms. In other words, where are the electrons arranged in the atom? The properties of the elements are determined by the arrangements of electrons in their atoms. It's kind of funny, huh? Because the electrons make up none of the mass. If you remember our last video, electrons are responsible for like none of the mass. The mass is all nucleus, protons and neutrons, but the electrons kind of determine how the atom is going to react. So the electrons are not totally free to move around, but instead they're restricted to certain regions of space called orbitals. Right? We'll talk more about this in a second. Let me just re-say that. The electrons are not totally free to move around at will, but they're restricted to certain regions of space called orbitals. Okay? Also, electrons, their energies are said to be quantized. Quantized means you can only have certain discrete, finite energy levels. For example, if I were to walk up a ramp, right, I can walk up an infinite number of increments. I can break that up into infinite number of increments. If I walk up a flight of stairs, however, those are quantized levels. I can only walk up those increments at a certain time. Okay, so when something is quantized, you have a defined set energy level increase. Okay, so that's kind of what I mean by the energies being quantized, is they are discrete certain levels. All right, So let's now move on and talk about identifying an electron and where it's likely to be found. I'm going to talk more about that new word up there called orbitals. Identifying an electron. Where is it likely to be found? Right? Atoms have a lot of different electrons in them, right? So we have to know where each electron is located. We have to know its address. So for example, let's compare a person, all right, you or me or your neighbor, gives his address within a state. All right, an electron can be found by giving its own address. So I can narrow down where a person lives. Give me your state. All right, you're in California? Okay, well, what city in California? Oh, you're in that city. Well, which neighborhood? Oh, you're in that neighborhood. All right, well, then which street? Or what's your house number? You can whittle it down and you can start to define where each person lives that way. Same thing with electrons, right? We have a great thing called principal quantum number n, then we have the orbital, and then we have the magnetic spin and things like this. So there's very similar to people, we can narrow down where each electron is located in an atom. So let me put all of that down in our notes. It says, for an electron, the quote-unquote address is composed of successively narrower categories. Number 1 is the shell, 2 is the subshell, and 3 is the orbital. So what do these 3 brand new terms mean? All right, number 1, shell. Shell is kind of like the energy level. It's a grouping of electrons in an atom according to their energy. Okay, these are given the variable letter N. N is in Nancy. Not too important for our course, but shell is a grouping of electrons in an atom according to their energy. So electrons are grouped around the nucleus into shells. If you remember earlier, I drew these concentric circles around the nucleus of the electron orbits. That's kind of like different shells. The n equals 1 shell, n equals 2, n equals 3, n equals 4, and so on. All right. So electrons are grouped around the nucleus into shells, which are like the layers of an onion, according to the energy the electrons contain. Now, the further the shell is from the nucleus, right, the more electrons it can contain. So we have the n equals 1 shell, n equals 2, n equals 3, n equals 4, and so on. We usually go to about n equals 7. And the further we get out, that's the larger shell, higher energy level, more electrons can be contained in those energy levels. Now the shell number n, I mentioned this previously. Shell number n, I'm going to make a little table here for you. So we're going to have shell number n, and then the number of electrons max we can get into that shell. So for the n equals 1 shell, we can only get 2 electrons max in there. For the n equals 2 shell, we can get 8 electrons max. For the n equals 3 shell, 18 electrons. And then for the n equals 4 shell, or the n equals 4 energy level, we can get a maximum number of 32 electrons in there. And I'm going to elaborate on what I mean by that when we start to talk about electron configurations, which is later on in this video. So now we need to understand what the second new term means. Number 2 is subshell. Subshell is often referred to as a grouping of electrons in a shell according to the shape of a region of space that they occupy. So let me say that in real time here. Subshell, it's a grouping of electrons in a shell according to the shape of a region of space they occupy. So the number of subshells is equal to the shell number. All right, so here's what I mean by that. I'm going to make another table. So shell number n, that's kind of the same row we just made. So n equals 1, n equals 2, n equals 3, n equals 4, just like last time. Except now we have a subshell designation. All right. So n equals 1, when my n is equal to 1, when I'm in the energy level of 1, I can only have something called an s subshell or an s orbital. When n equals 2, I can have an s orbital or a p orbital. When n equals 3, I can have an s orbital, a p orbital, or a d orbital. When n equals 4, my subshell designations or my orbital identifiers can be s, p, d, or F. So there are 4 types of subshells that increase in energy, and they go from S to P to D to F. Now I know a lot of this is obscure. A lot of this I just want you to have the information in your notes so that you can refer to it if you have to answer the homework problems. All right, I'm trying to give you background information before we can assign electron arrangements or electron configurations, which is how we identify where every electron is in an atom. So let's bear with some of this background for right now, okay? I know it's obscure. Number 3, orbitals. These are regions of space within an electron where an electron in a given subshell, S, P, D, or F, is likely to be found. You can never really identify where the electron is, but you can have an idea. The S subshell has 1 orbital. P subshell has 3 orbitals. The D subshell has 5 orbitals. Just think odd numbers here, right? 1, 3, 5. What's the F subshell? 1, 3, 5, 7 orbitals. So there are 7 F orbitals. There are 5 D orbitals, or subshells. There are 3 P subshells, or P orbitals. And there's 1 S subshell, or S orbital. Subshells and orbitals are kind of like they're basically the same word. Okay. Now each orbital or subshell can hold a maximum of 2 electrons. All right. Now I just got done saying 1, 3, 5, 7, right? So if you double that, you end up with 2, 6, 10, and 14. More on that in a second. Okay. So example. What's the maximum number of electrons occupying the following subshells? In other words, what's the maximum number of electrons occupying the following orbitals? Subshells and orbitals are kind of like synonyms. The 3p subshell, the 2s, and the 2p. Well, the 3p subshell, it says you can get a maximum number of 6 electrons in the 3p orbitals. But I thought you can only get 2 electrons max in an orbital. Well, that's correct, but how many orbitals are there if it's the p subshell? There's 3. So if you have 3p orbitals, you can get 2 electrons in each of those 3p orbitals, total of 6 electrons. All right. Now the 2s subshell. If you remember the S subshell, there's only 1 of those, so 2 electrons max. The 2p subshell is no different than the 3p subshell. It's just further away from the nucleus. So the 2p subshell, the answer is the same as a 3p. You got 3 2p orbitals, so 3p orbitals, 6 electrons total. All right. Next example. How many electrons are present in an atom with filled 1s, 2s, and 2p subshells? All right. And then we want to name the element. So 1s, I can get 2 electrons. The 2s, I can get 2 electrons. Remember, an s orbital can hold a maximum of 2 electrons. P orbitals hold a maximum of 6. Don't worry too much about the big number coefficient in front of the s, and the p. All right? That's 10 electrons total if you add up the 2, 2, and 6. 10 electrons on the periodic table, that's neon. You just go and find the atomic number 10. All right. Now, all the stuff I've talked about in the last, 3 or 4 pages, I know it's tough to digest. It's obscure. It makes no sense. And I know that you're going to rewrite it later, and that will help make a little bit more sense. But really, that's just the background. That's the language we need in order to be able to speak what I really want us to talk about, which is how to write electron configurations. Your book calls these electron arrangements. Electron configurations are electron arrangements. And they tell me where every electron is in an atom. All right. So writing electron configurations or writing electron arrangements is the address of the electrons in an atom. All the obscure stuff we just now got done talking about is so we can do something like this. All right. When electrons fill in to their configurations, they do so according to the diagonal rule. So you need to know how to draw this. It's a 1s, 2s, 2p, 3s, 3p, 3d, and then when you get to the row 4s, 4p, 4d, 4f, you just repeat for 5, for 6, and for 7. And if This is drawn very neatly because I have to draw my arrows appropriately. Through the 1s, through the 2s, through the 2p3s, then I go through the 3p4s. If you practice writing this, this is how you are going to assign the electron arrangement or the electron configuration based on the number of electrons you have in an atom. So we're going to find out how many electrons your atom has. Okay, so if I give you an atom, you find out how many electrons it has, and then you put them into their orbitals according to the following diagonal rule chart. Remember, see the vertical S's, 1s, 2s, 3s, they can hold 2 electrons. See the vertical 2p column, the second column, they can hold 6 electrons total. The D's, there are 5 d orbitals, which means 10 electrons max. And then on the very far right, the 4f column, 14 electrons max. So look at magnesium. Magnesium is atomic number 12. So if it's got 12 protons, it's also got 12 electrons. So we assign it 1s2, 2s2, 2p6, 3s2. That's my electron configuration, or as your book calls it, electron arrangement for magnesium. You see the exponents? 2, 2, 6, 2, 2, 4, 10. My exponents add up to 12. I know I've done this right. Okay? So that is an electron configuration for magnesium. In other words, it's an electron arrangement. Another way to write this is something called orbital notation. So I'm just drawing that 1s orbital. I'm drawing the 1 2s orbital. I'm drawing my 3 2p orbitals and my 1 3s orbital. This is another way to assign the electron arrangement or the electron configuration, right? There's actually a third way, which we'll get to a little later on. All right, let's do more examples so that some of this makes sense, okay? Write the electron configurations. Remember, your book calls this electron arrangements. Write electron arrangements or electron configurations for the following: carbon, sodium, Cl, and Ca. So hopefully we know that carbon is atomic symbol C. We look up C and it's Z, or atomic number. Number of protons is 6. Atoms are neutral, so it's also got 6 electrons. 1s2, 2s2, 2p2. The exponents add up to 6. Sodium, Z equals 11, so 11 electrons also. 1s2, 2s2, 2p6, 3s1. If you say these out loud, you begin to realize, hey, I can fill these up without using the diagonal rule. I know how it goes. Chlorine, 17 electrons. So the exponents will add up to 17. 1s2, 2s2, 2p6, 3s2, 3p5. You notice the 3p5? I can have a total of 6 electrons in the p orbitals. I didn't need 6, I only needed 5. Calcium, 20 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. How did I come up with these? I just followed the arrows in the diagonal rule. Okay. If you look at the B, sodium, see how it says 3s1? I could have had a 3s2 at the end of sodium up there in B, but sodium only has 11 electrons, so it stops at 3s1. Okay. That would be a half-filled s orbital, right? Let's put that last one, D, calcium, into orbital notation. Some people like orbital notation better. I want you to focus on how I fill in those 20 electrons. See this? Boom, boom, boom. For 2p and for 3p, I singly fill them up first. 2p and 3p, those are degenerate orbitals. And electrons are negative, right? So you want to give them their own box before you come back, because a negative and a negative are going to repel. All right. Example. More of the same. Write electron configurations for elements with Z equals 14 and Z equals 26. Well, Z equals 14, we have to go find it. It's silicon, Si. And for Z equals, oh, it's 36. Sorry, not 26. 36 is Kr, krypton. Silicon is 14 electrons. I begin using the diagonal rule. 1s2, 2s2, 2p6, 3s2. I could have done 3p6 total, but I only needed 3p2. Stop at 14. My exponents add up to 14. Kr, 36 electrons. See how these become redundant? 1s2, 2s2, 2p6, 3s2, 3p6. You might want to stop and check at 3p6. All right, I need to keep going at 3p6, 4s2, 3d10, 4p6. All right, and just a note there on that 3d10, look how I filled them up. Singly first, then I come back and match them up, gives me 3d10. I still needed 6 more electrons, so I went to the 4p's. All right, we're going to do more practice on these. Lots of homework on these electron arrangements. Some of that background information I gave you in the beginning to the middle of today's video, I know just as much as you do how obscure and how hard it is to understand that. Just have a sort of an understanding that that's the language we need in order for me to talk about a 1s orbital can hold 2 electrons. A 2s orbital can hold a max of 2 electrons. I'm looking at the last one here. 2p, 3p, 4p. A 2p and a 3p and a 4p are the same thing. They can hold a maximum of 6 electrons. First time you've seen a D there happens to be 3d, but a 4d, a 5d, they can hold a maximum of 10 electrons. All right, so maybe in the third week when I do some homework problems as a video to show you some of the homework, in week number 3, I'll start to do some of these for you, okay? But that's it for this week. There's only 2 videos for week 2, all right? You do have a quiz at the end of this week that you need to start and finish, all right? Make sure you go to Canvas and read about how the quiz is done. It is timed, so more about that in the Monday lecture for Tuesday, all right? So email me through Canvas or just via email, jketchum@ivc.edu, and we'll take care of it. All right.